All right, so this AP problem looks a lot like that elevator experiment we did, but with sort of idealized data, so you can actually do the calculations. All right, so there's a lot of parts to this one, but most of them are kind of redoing the same thing, so it's not as bad as it might first look. First thing, right, we have a free body diagram on the person. So at 8 seconds, right, we're told his normal weight is 500 newtons, and at 8 seconds, the scale reading is a little bit bigger than that. Right? So when I draw his weight vector down, and that was not straight, and his force of scale, or the normal force, I should make sure to draw that the normal force of the upward vector, whatever that might be, has to be bigger than the weight, right? Because that matches the description at 8 seconds. Right, so only two forces, right? He's not moving horizontally at all, so there's nothing happening there, just vertical forces. All right, so that's part A. All right, part B. Once you do one of these time intervals, you've really done all of them, right? So to describe the acceleration of the elevator, what we really want to do is use Newton's second law, right? The net vertical force relates to the vertical acceleration. Right? Clean that up because that's kind of sloppy. Right? And we just did the free body diagram, so the net vertical force is easy to find. The upward force is the force of the scale, or that scale reading from the graph. And the downward force is his weight, which we know the number of, 500 newtons. And so if we want to solve, we're just going to rearrange, right? AY is FS. I know the definition of weight is mg. Actually, I don't even need to use that. I have the weight directly. I'll just leave it like that. And we divide by m. Okay? So the other thing, right, we don't have the mass directly, but we know, I need to figure out this. So we know that, actually, let's do it this way. We know that W equals mg. So m is W over g is 500 divided by 9.8. 9.8. So we can find his mass, and we should make sure to do that. And if you plug those numbers in, you get 51 kilograms. All right, so now we've got his mass. Fantastic. So we can calculate his acceleration at any given time. Right? This number is just what's on the graph. Right? From 0 to 5 seconds, the scale reading is 500 newtons. The weight, this is always 500 newtons. And the mass, right, we just found, right? We did that side calculation. And so all we're going to do is we're going to plug this in for 4 different Fs values, right? So from 0 to 5, right, the force of the scale is 500, his weight is 500, and so that's just 0. Right? Pretty straightforward. From 5 to 10, we have 700 minus 500 all over 51. Right? And if you plug that in, you get 3.9 meters per second squared. From 10 to 15, it's 500 minus 500 51 again, which is 0. Right, don't forget units. From 15 to 20, we have 300 minus 500 over 51, which is going to be a negative 3.9 meters per second squared, right? So once you start with this and get to that result, you've really solved it, right? The rest is just reading graphs and numbers correctly. Right, so you should have 0, 3.9, 0, and then negative 3.9 for the 4 time intervals. And then, right, if you've done those values correctly, the graph should be really easy, right? Because all you're doing is you're applying the values that you had. Right, this is the acceleration, this is time, and each tick mark is 5 seconds. Then we have 0, a positive 3.9, 0, and then a negative 3.9. I still can't draw straight lines that well, right? Right, and so like they gave the tick mark at 5, so it should look kind of like that, right? But again, the graph should be easy once you've done the calculation correctly, right? If you do the calculation carefully, then the graph is simple. Okay, so the velocity at the end, it's a little bit more involved, right? A little bit more involved. But we know from the kinematics equations this statement, right? And we also know that we start at rest, right? So, for the first 5 seconds, at the end of the 5th second, our final velocity is we start at rest, we have 0 acceleration, and it lasts for 5 seconds. So at the end of 5 seconds, we're still not moving. At the end of 10 seconds, we still start at rest, right? That's this value right down there. Actually, let's do that in a different color. Right, that's this value, right? We start the 5 to 10 seconds motion with what we ended the 5 seconds with. Now we have an acceleration, right, from what we found in part A. Right, so we can plug that in, and we get 19.6 meters per second. So V15, we start with what we ended the 10 seconds with, so 19.6, and we have 0 acceleration from 10 to 15 seconds. Oops. Right? And then finally V20, we again start with what we ended with, and here we have another acceleration, but it's a negative, right? Negative 3.9 times 5. Oops. And if you plug that in, you're going to get right back to 0 meters per second. Right? So again, all this is about organizing information. Once you recognize that equation, you just plug in numbers very carefully. And once you've done that, the graph should sort of do itself. Next, all we're going to do is we're going to plot those numbers, V and T, 5, 10, 15, 20. So from 0 to 5, velocity is 0. From 5 to 10, at the end of 10 seconds, we know we're up at like 20 meters per second. And we know with a constant acceleration, the velocity must be linear, so I need a linear shape. Then from 10 to 20, it doesn't change because there's no acceleration. And then from 10 to 15. From 15 to 20, it goes right back to 0. Right, so it should look something like that. Okay. Last part, the toughest part, dealing with displacement. But once again, kinematics is our friend. If we know the velocities and accelerations, we can find the distances, right? We have the kinematics equation, x equals x naught plus v naught t plus 1/2 a t squared, right? So, at the end of 5 seconds, we start at the origin, x equals 0, we're told that in the problem. We know the initial velocity is 0, right? We calculated that in part C. And we know the acceleration is 0. Right? So, at the end of 5 seconds, we have not moved. At the end of 10 seconds, we take this as our starting position. So 0. We still know, again, from part C, the initial velocity is 0. Now, though, the acceleration is not 0. Right? So it's been 5 seconds with that acceleration. And so you plug those numbers in, and you get 48.8 meters. Right? So at the end of 15 seconds, we take our starting position. 48.8. We know our initial velocity from part C, 19.6 times the time, 5 seconds. And then we have to add the acceleration, which in this case is 0. Right? So we plug all that in. And if we plug that in carefully, we get 147, actually. Right? 147 meters. And then finally, where are we after 20 seconds? Well, once again, we just take that straight down for our initial position. Our initial speed at starting 20 seconds is again 19.6, so that's times 5. And then we have an acceleration here, right? 1/2. It's a negative acceleration, t squared. So we plug all that in very, very carefully. And if you do that, you should get 196 meters. Right? All right, so that's a little bit tougher of calculation, but again, it's just identifying the equation and then plugging in the numbers. Now, the graph on this one is definitely a little bit tricky. Right? But we know a lot of stuff. So I'm going to call this x and t. So we know for the first 5 seconds, oops, let me add those 5, 10, 15, 20. We know for the first 5 seconds we don't move at all. Right? That part is straightforward. From 5 to 10 seconds we have a constant acceleration, which means that the graph must be curved. Right? Like a parabola. Right? Because we have, again, to identify where there's a t squared, right? So it has to be a parabolic shape. During 10 to 15 seconds, here the acceleration is 0. That means that the velocity is constant, or the position graph is linear, right? Notice how there's t to the first, so it's got to be a linear shape. So instead of curving up, it just keeps going in a straight line, roughly speaking. And then, from 15 to 20, we're back to a parabolic shape, right? Because it's t squared. But we have a negative sign, which means it's a downward curving parabola instead. So it has to do something kind of like that. Okay? So that has to be what the shape is, and right, you should make sure the numbers all match up. So, actually that's a bad color. So this is linear, and these are quadratic. Okay? And so there are a lot of steps to this problem, but as you see, many of them are really, really easy. It's critical to organize your work and be careful with it, because if you do that, even making some mistakes on the graph won't really kill you, because you've done sort of the easier stuff well.